Good day to all, I am Lexter Tacgos and I will discuss motor protection relay. Electric motors are the workhorses of industry, converting electrical energy into rotational mechanical energy. As we can notice, most modern industries uses electric motors for them to produce or manufacture their products in an easier and faster way. In squirrel cage induction motor, there is a particular type, the TEFC type, totally enclosed fan-cooled, that became extremely popular mainly because of their simple, rugged construction and good starting and running torque characteristics. Aside from these positive traits, because dust and moisture are kept out of the bearings and windings, the TEFC design extends the mechanical life of the motor. And when used correctly, this type of motor has proven to be extremely reliable with an expected lifetime of up to 40 years. So we can understand why industries choose this type of electric motor, the TEFC type, because aside from its reliability, its life expectancy, the design itself tends to extend the mechanical life of the motor as it prohibits dust and moisture from coming inside of the motor. This is the pie chart for main causes for motor damage in industrial drives, and as you can notice, 30% goes to insulation faults, followed by long-time overheating 26%, rotor or bearing fault with 20%, other causes 19%, and faulty protection 5%. As we go through my presentations, we can reason out why insulation fault got the big portion of the pie chart and the reason why of the other four main causes. This is the pie chart for the protective functions needed to detect the motor drive faults. So 30% we have short circuit and earth fault protection, followed by thermal overload protection with 26%, starter supervision and thermal sensor unit with 20%, 19% for other protective functions and detectable faults, and 5% for continuous self-testing of the protective relay. So these are the protective functions we needed when we are dealing with motors. The life of an electric motor is determined by the shorter of the following two factors. First, we have the mechanical life. The life of the mechanical parts such as bearings, shaft, fan, and the frame, and it depends on the environment such as dust, moisture, chemicals, etc., vibration, and lubrications. So this is one of the reasons why industries choose TEFC type of electric motor, because TEFC designs prohibits the entrance of dust and moisture. And for that, it extends the mechanical life of the motor. The next factor is electrical life. This is the lifespan of the electrical components in the motor connection box, such as the stator winding and insulation, the rotor winding, and the cable terminations. Early motor protection relays. Early motor protection relay designs had a single function, and that is only to protect the motor from overloading by ensuring that it never drew more than the rated current. So yung pinaprotektahan or yung function lang niya, single function lang ng early motor protection relays is to protect the motor from overloading and making sure that it never drew more than the rated current. Next is that in the past, it was common practice to detect overheating using temperature-dependent elements built into the motor's winding. So we can see at the picture yung temperature-dependent element natin is naka-attach doon sa stator winding natin, doon sa coil natin. But the other side or the negative side of it is that it is unsatisfactory because it is obtained indirectly from the current conductor rather than directly from the current conductor, resulting in significant sluggishness. So hindi naka-attach directly yung temperature sensor natin doon sa current carrying conductor, and naka-attach lang siya doon sa insulation nun. So there is a difference on the result of the temperature sensor when we attach it on the insulator compared doon sa kung i-attach natin mismo doon sa current carrying conductor. In some cases, bimetallic thermal overload relays do not provide complete protection because they do not have the same thermal heating and cooling characteristics as the motor they are protecting. We all know we have a lot of motor being sold in our malls and the market. And for that, those motors comes from different manufacturers, and those manufacturers have the freedom to pick what type of metal, what kind of metal they're going to choose, what type of conductor they're going to choose to build up their product. And for that, there is no universal type of metal na gagamitin for the universality of the motor. And for that, the metal that being used in the bimetallic strip might not be the same with the metal or the conductor being used with the motor. And for that, there is a discrepancy when it comes on the thermal heating and cooling characteristics of both metal. To further discuss this, we have this graph. The graph shows typical temperature curves of the winding temperature in solid lines compared to the heating and cooling curve of the protective device, the dotted line. So as you can see first from the first quarter, first 5 to 10 seconds, nag-unang uminit yung protective device natin or yung bimetallic material, and then sumunod yung winding temperature natin. And as you can notice here, kung ang rating or yung rate ng bimetallic material natin is at 170, magti-trip na siya. So, it's going to trip na. So it's like nag-trip na yung protective device natin without the winding temperature exceeding its limit pa. So, there's a inaccurateness when it comes on tripping on this graph in this 5 to 10 seconds. When we go look for the big picture naman, we can see na there is a drastic change. Yung protective device natin in dotted line is minimal lang yung change when it comes in graph, while yung winding temperature is malaki yung pag-iba. Malaki yung pagkakaiba niya from the first peak to the second peak up to the third peak. So, if we conclude this, if we watch this graph, we can say on this second peak pa lang, nandito na yung protective device natin. Ganito nakainit yung protective device natin without knowing na winding temperature natin is above na pala doon sa protective device natin. So, kung dito sa first picture, kung dito sa first 5 to 10 seconds natin, pwedeng mag-trip na yung protective device without exceeding the winding temperature limits, kahit hindi pa niya naabot yung limit niya, nagtitrip na. Dito naman sa second peak is that hindi pa nag-trip yung protective device natin pero umabot na or nag-exceeds na doon sa limit ng temperature ang winding temperature natin. So, there's a little discrepancy when we compare the winding temperature to the protective device temperature of early motor protection relays. Steady state temperature rise. Electrical machines should be loaded as close to their permitted operating temperature limit as possible for maximum efficiency. When we are buying, or if we want to buy a motor, ito yung isa sa mga hinahanap natin. What is the maximum efficiency of that motor? And to reach this maximum efficiency, if we want to reach this, we should load the electrical machines that it results to the operating temperature of it, pero dapat hindi mag-exceed doon sa operating temperature limit ng machine na yun. But excessive thermal stressing of any significant duration, on the other hand, must be avoided if the installation's life is not to be shorted. So, dito napapasok yung pinakamalaking portion ng pie chart natin, yung installation's fault. Kasi, when we tend to abuse machines or motors specifically, kasi nga, like for example, we have a lot of orders, we have a lot of orders, and then yung order natin is dapat dumating na sa kanila on this time, and as you can foresee or as you can As you see na hindi siya aabot if ganitong work lang yung gagawin ng machine. Therefore, iisipin ng tao na okay, sa ganito lang na time, na duration for one day lang, magiging ganito yung machine natin na i-exceed natin yung, or yung almost ma-reach na niya yung limit niya. Kasi meron pa minsan meron tayong ganong mentality na okay, ganito. Ngayon ko lang naman to gagawin. So maybe maliit lang yung negative effect na mangyayari sa kanya. But on the second sentence, excessive thermal stressing on any significant duration. So any significant duration, either it's on how many seconds, the insulation might melt, and once the insulation melt, it can go through short circuit, and once it's short circuited, it is a dangerous stage na for that motor to operate. So that's why masisira na yung motor natin. The temperature of a motor will rise exponentially due to dissipation of the heat to the environment or cooling medium towards its respective operative temperature under steady state conditions. Thermal time constant. The time constant tau is defined in IEC 255-8 as the time in minutes required for the temperature of a body to change from an initial temperature to 63% of the difference between initial temperature and the new steady state temperature. Unfortunately, the thermal time constant tau of the motor is frequently not known. Motor current in start and stall conditions. When we are asked to evaluate and give parameters, what type of overload relay or overload motor relay yung bibilhin ko for this type of circuitry na merong motor connection. So, when we are calculating, we must assume, or it can be assumed, that the motor starting current remains constant and equal to the standstill value throughout the starting time. And if we follow this, we can have a maximum protection. It's better to have maximum protection than minimum protection. Stalling motors. A motor stall when running or be unable to start because of excessive load. It will draw a current from the supply equivalent to its lock rotor current. So, nangyayari itong stalling motors when yung force na kailangan ng isang bagay to lift is hindi na kayang ibigay ng motor natin. Like for example, yung mga crane. What if we're going to lift below the maximum weight na kayang i-lift nung crane, we can lift it. But once mag-exceed na doon sa maximum yung i-lift ng crane, possible is that masisira yung crane, mag-stop into halt yung operation ng crane, and that can cause to human na nag-ooperate nun and then dun sa motor or dun sa machine na ginamit nila. Most loads cause normal induction motors to start in less than 10 seconds, while the allowable stall time to avoid damage to the motor insulation is greater than 15 seconds. So this is the first graph when the relay can give stall protection, and the condition is that the relay operation time must be less than the stall withstand time. And this is the graph for the relay where it no longer can give stall protection when the condition is that relay operation time is greater than the stall withstand time. Unbalanced supply voltages. A three-phase motor's voltage can be unbalanced for a variety of reasons, including single-phase loads, blown fuses and PF capacitors, and so on. Furthermore, if a one-phase lead in the supply to the motor is accidentally opened, the motor will continue to run even though it is only powered by two phases. Pero, as what the name of the motor, three-phase motor, it must be supplied with three-phase system. So, even though it's still run, but it may not be good for the motor. Like for example, simple analogy is that you are living in the Philippines with 220 or 230 socket, and you're going to plug an appliances from America with 110 volts rating 50 hertz. So ano yung mangyayari doon sa appliance natin? Puputok. And then magti-trip yung breaker natin. So for that, we must be aware. We must be aware and careful when it comes on dealing with three-phase motors voltage. We must secure na all three-phase are working and they are supplying to the motor. And it should be remembered that it is not the relatively much larger negative sequence component, that it is the relatively rather much larger negative sequence component of the unbalanced current caused by the unbalanced voltage that is important, not the unbalanced voltage itself. Mas mahalaga yung unbalanced current than the unbalanced voltage itself. So determination of sequence currents. There is no fixed relationship between the positive and negative sequence currents in the general case of unbalanced three-phase voltages. The actual value of the negative sequence current depends on the degree of unbalanced supply voltage in the machine's negative to positive sequence impedance ratio. The ratio can be calculated using the induction motor's general equivalent circuit. The rating due to unbalanced currents. So we discussed about the unbalanced voltage, and we know na that it is not the unbalanced voltage that is important, but the unbalanced current na nabibigay ng unbalanced voltage. The negative sequence component of the current does not contribute to the motor's driving torque. In fact, it produces only a minor negative torque. However, for a voltage imbalance of the order of 10%, the magnitude of the torque due to the negative sequence current is usually less than 0.5% of the full load rated torque and can thus be ignored. As a result, the presence of negative sequence currents has little effect on the starting properties. So, when we're talking about starting properties, yung paano mag-start yung isang motor, the negative sequence current or the unbalanced current has a little effect on it. But the main effect of negative sequence current is to increase motor losses, particularly copper loss, thereby reducing the machine's available output if overheating of the machine windings is avoided. So, when we introduce when we introduce unbalanced current to the motor, we tend to increase the copper loss. And for that, when the copper loss increases, the heat produces by the loss is increased as well. So as the copper loss increases, also the temperature increases, and thereby it overheats the machine. And hindi naman natin gusto na mag-overheat yung machine. So we tend to pull it off or cut it off out of the supply. Therefore, we cut the maximum output of the machines. Electrical fault in stator windings, earth faults, face-to-face faults. First, what is faults? Faults in the motor windings are primarily earth faults caused by a breakdown in the winding insulation. This type of fault is very easy to detect by using an instantaneous relay, typically set to approximately 20% of the motor full load current and connected in the residual circuit of 3 current transformers. So, as we read the first sentence, faults in the motor windings are primarily earth faults caused by a breakdown in the winding insulation. So that is why insulation faults have the big part in the pie chart natin, doon sa main causes. Kasi nga, it is the usual problem, yung pag-melt ng insulation. And once ma-melt yung insulation, nagtatouch na doon sa iba. Doon sa ibang coil. And for that, we have this kind of fault, nagiging short circuit. So, ganun. Next, face-to-face faults. Between phases are uncommon due to the relatively greater amount of insulation between phase windings. But sometimes, though it is not common, but sometimes when we overuse a machine and we exceeds the temperature limit, we are melting the insulation, and afterwards, when it is already melted, the the conductor can attach to one another and can cause fault. But it is a very uncommon because we are very careful when it comes on temperature in a motor. Differential protection is sometimes provided on large and important motors to protect against face-to-face faults. But if the motor is connected to the unearthed system, it does not appear to be of great benefit if a fast operating and sensitive earth fault is already provided. Terminal faults. To protect against phase faults at the motor terminals such as terminal flashovers, high-set instantaneous overcurrent relays are frequently provided. When configuring these units, care must be taken to ensure that they do not operate in the initial peak of the motor starting current, which can be 2.5 times the steady-state RMS value. Typical protective setting for motor. So first we have this long time pickup. 1.115 times motor full load current times motor service factor for applications encountering 90% voltage dip on motor starting. 1.25 times motor full load current times motor service factor for applications encountering 80% voltage dip on motor starting. Next is we have long time delay. Greater than motor starting time at 100% voltage and the minimum system voltage, less than lock rotor damage time at 100% voltage and the minimum system voltage. On high inertia drives, it is common for the start time to be greater than the lock rotor withstand time. Under these circumstances, set the time to permit the motor to start. Supplemental protection should be added for lock rotor protection. One example of this is a speed switch set at 25% of rated speed, creeping through a timer to trip if the desired speed has not been reached in a predetermined time. Next, we have the instantaneous pickup, not less than 1.7 times motor LRA for medium voltage motors, not less than 2.0 motor LRA for low voltage motors. B. Ground fault protection. The minimum pickup and minimum time delay for static trip units, core balance CT, and 50 relays set at minimum for medium voltage, low resistance grounded system. Residually connected CT and 50 over 51 for medium voltage, solidly grounded systems. Minimum top and time dial equals 1 for 51 relay. Minimum top not less than 5 amperes for 50 relay. That will be all, and thank you.